This presentation is a demonstration of an approach to digitalization and reasoning of engineering text data stored in spreadsheet tables. It is the result of ongoing collaboration between a team of engineers and computer scientists, including Tim French, Caitlin Woods and Tom Smoker at the University of Western Australia, and Johan Klua at DMVGL and the Sirius Centre in Norway. The voiceover on this recording is by me, Melinda Hodkowitz, and my colleague, Johan Klua. The motivation for this work is obvious to anyone who is working as an engineer in industry today. Spreadsheets are the default way for engineers to capture and share data. A vast amount of knowledge is locked away in this format. This data is in a digital form, but it's not machine interpretable. This limits its use for artificial intelligence and other digitally based applications. A number of tables made by engineers have an implicit structure. The engineers know how the columns are related to each other. However, there is no written or separately documented schema. In this slide, for instance, the engineer knows that subcomponent is a part of component, and failure effect refers to the failure mode of the subcomponent. However, there is no formal schema that captures this knowledge to somebody who is perhaps not an engineer or familiar with this particular process. The structure and column headings used are often driven by engineering standards or headings adopted by widely used relational databases. It is not uncommon to find very similar headings for the same process across many different companies, as shown here using failure modes and effects analysis as an example. Another example is the way in which we capture equipment hierarchy. On the left is a figure of an HVAC subsystem from the IEC standard for failure modes and effects analysis. On the right is how, as engineers, we capture the relationships between levels in the asset hierarchy. Note, nowhere are the relationships is part of or has part, the sorts of relationships commonly captured explicitly in knowledge graphs and ontologies, actually made explicit here in the table. Our use case is a widely used risk assessment process called Failure Modes and Effects Analysis, or FMEA. A manufacturer of engineering products will have at least one for each product, and often more than one. FMEA also forms the basis for maintenance strategy development for process and infrastructure operators. Engineering organizations can have the results of hundreds of FMEA workshops locked away in spreadsheets. This knowledge is incredibly expensive to collect in terms of experts' time and is a valuable source of understanding about the asset and its failure behavior. So our question is, can we extract the implicit knowledge captured in the FMEA tables to support quality control of the FMEA process? So for a start, what do we mean by implicit knowledge? Many of you watching this video will be familiar with the FMEA process. One of the key outcomes is to understand the effect of a failure. This effect is assessed first on the function of the asset itself. Will the failure of a bearing cause a functional failure of the pump in which it is installed? Assessing the effect of a component on its system requires knowledge of the configuration of the system. For example, there may be 2 fans in a cooling system, but only one is necessary for the system to function. This knowledge is captured implicitly in the asset hierarchy and can be combined with the FMEA data to enable inference. We shall demonstrate this later in the case study. Our answer to the question, can we capture implicit knowledge, is that we can, using well-established ontology concepts. An ontology is an artificial language designed to be understandable to both people and computers. The leading standard for ontologies is called Web Ontology Language, or OWL, and it's provided by the World Wide Web Consortium. The latest edition came out in 2012, and it is supported by a large and growing ecosystem of software and methodology, including tools for mapping spreadsheets into structured and explicit forms. So how do we start? First, we assess the datasets. In our case, there are two, the asset hierarchy and the FMEA tables, and we identify concepts and their relationships to each other. For example, we can see on the right-hand side the relationship between the heater and the heating system in the table is captured in the text as F equals heater system, has functional part, heater. Writing in this way makes the text machine readable. Next, we decide on an upper ontology to align our work to. We use ISO 15926 Part 14, an AL-DL top-level ontology. This is necessary to allow our work to be interoperable with other ontologies using 15926 Part 14, such as those developed at the Sirius Centre in Norway. This alignment is important, and it sets our work apart from previous efforts to make FMEA ontologies that have not aligned to an upper ontology and hence are not interoperable. The next step is to define individual domain-specific modules and populate these modular ontologies with classes, relations, and axioms required to capture the concepts described in our data.
What makes ontology more powerful than a regular industrial dictionary? When an asset is described in the language we build, we obtain a knowledge graph type database. The computer can use this to derive implicit facts in so-called automated reasoning. Unsurprisingly, there are limits to what the computer can understand, but practical experience with ontologies shows that we can effectively offload work that is trivial, but complex and time-consuming. This not only frees up time for specialists to focus on the novel aspects of an asset or process, we can be sure that the computer will never miss an inference that follows from the knowledge base, allowing us to be more confident that our FMEA analysis is complete. In an industrial setting, we need vocabulary for characterizing the physical asset, the composition of its functional systems, and the processes it executes. That is a basis. For this demonstration, we extend the language to allow for not just functions to be captured, but also malfunctions, as identified during the FMEA risk assessment process. Crucially, as we build the vocabulary, we implement category distinctions that allow facts to be used in automated reasoning. We separate functions from the objects that have them, events from their observations, and so forth. The industrial ontology needs to be designed as a hierarchical structure, proceeding from modules that are wholly generic down to specialized terminology and finally to a detailed description of the asset under consideration. In this study, a greatly simplified terminology was applied, but in real-world applications, we will typically see tens of thousands of terms across many modules, combining the terminology and rules of industry standards as well as product catalogs into a knowledge base. A functional system ontology provides a language for characterizing an asset in its functional breakdown, with systems and subsystems down to the level of components. This will typically draw on a variety of industry standards. Next, for the FMEA ontology, we add the terminology of failure modes. The ISO 14224 standard for reliability and maintenance is a primary source for this vocabulary. Armed with the generic vocabulary, we are ready to map the spreadsheets that describe the specific individual asset under consideration into facts in the ontology language, its composition into functional units, as well as the ways these units may be expected to fail during operation, as uncovered by the FMEA analysis. The functional system ontology provides a language to describe systems at various degrees of granularity. This is our functional breakdown from the function of the asset as a whole down to a level of component that is not detailed further. The functions of the system and subsystems, in our example case heating and cooling, are realized when processes are carried out by the asset. The functional breakdown describes the intended processes, how the asset is supposed to work. For the FMEA risk assessment, we enrich this description with malfunctions as realized in unintended processes. We wish to identify how failures will propagate from subsystems to affect the performance of the asset. We explicitly state how higher level functions depend on subsystems and components working correctly. Automated reasoning then allows the computer to infer what the impact of failures will be on the system as a whole. The following slides illustrate how the computer handles propagation, given input to the effect that the malfunction has occurred. The inference mechanism itself is in no way novel to our proposal. We simply apply the capability provided by the OWL-DL standard. If our representation is sound, what the computer infers will correspond to what an expert would say. Here is an example. From our risk assessment, we know that the heaters component has a potential malfunction, a disposition to fail, given overcurrent. When we provide input to the effect that the malfunction is in fact realized, the computer makes the inference that the heater is in a fault state. We can ask for an explanation why, and the inference steps will be laid out for us in the form of a proof. This may look trivial, but note that inferred facts serve as premises for further inference. This is the propagation mechanism, as we will see in the next slide. The computer has inferred that the heater's component is in a fault state. Reasoning from the functional breakdown, the computer further infers that the entire heating, ventilation, and cooling system must be in a fault state. When asked, it will list the facts and rules used to arrive at this conclusion. For our demonstration here, we have made the simplified assumption that fault state is always and unconditionally propagated from components and subsystems to higher level functional units. Of course, in real-world FMEA cases, we would be more nuanced, with different rules according to criticality.
We have not talked about the mechanics of transferring the data from the spreadsheet tables into OWL. A method to do this has been developed at the Sirius Centre using Otter templates, but discussion of these is beyond the scope of this paper. This paper makes the following contributions. First, we are raising awareness of the issue associated with valuable engineering knowledge, for example, FMEA, that is locked away in spreadsheet tables. We have demonstrated a process to extract this knowledge in a machine-interpretable way using modular ontologies. Further, we have used the power of ontological reasoning to test and infer relationships. Finally, we suggest that our work can be applied to FMEA data and asset hierarchies stored in spreadsheets in other organizations, unlocking this valuable data by making it machine-readable and usable. Thank you.